Thank you all for coming. So I am especially thrilled to introduce Dr. Kavitha Srinivas. If you're here, it means you saw her amazing credentials on the flyer or on LinkedIn or on Google Scholar, so I won't embarrass her and bore you by repeating a bunch of numbers. But I will share with you two things about her from when we were both working at IBM Research. This is where I get to embarrass her.
Time to hide.
So one thing I'd like to share is her group did a wonderful piece of work called Helix, which resulted in a paper at SIGMOD, which is the top academic conference in computer science for management of data. And if any of you, I'm sure the professors can relate to this, when you're doing research, one of the things you have to do is get funding. So I was working on a funded project with some of the software product divisions, and I heard about Kavitha's system, and I thought, oh, maybe it can solve some of the problems. And we had a meeting, you and the show, and we spoke about it. And much to her credit, after some discussion, they said, no, their system does not solve the problem that I was working on. Now, as a student, that's like, well, of course you're going to say that. But if you've ever been in research, trying to get funding, etc., it takes a lot of character to say, no, my research does not solve your problem. That's one thing that stands out in my memory. The other thing is, Kavitha was just not an individual researcher, which she was for a bunch of years. She was also the head of a research team. And you can judge a manager in any situation, and certainly in research, by who goes to work for that person. In general, to be a good manager, you have to have all kinds of interpersonal skills, social skills, political skills, business skills, etc. To be a good, successful manager in research, you have to have all of that, plus do excellent research. And judging by the people I know who went out of their way to join her team, and from what I know about her myself, Kavitha is a fantastic researcher, a fantastic person, and a fantastic businesswoman. So I am thrilled that she's come to speak to us today. And without taking any more of your time listening to me, here's Dr. Srinivas.
Thank you for having me. That was a wonderful introduction and somewhat uncalled for. Don't believe anything you just heard. I think he was talking about someone else. Anyway. What I'd like to do today is to spend the first chunk of time talking to you about what, in my view, a data scientist does. This is based on observations of data scientists in IBM. I was never a data scientist, so up front I'm going to tell you that's kind of a poorly defined thing anyway. Everybody calls themselves a data scientist, just like everybody says they're playing with big data when they're dealing with thousands of rows. Very common, right? But I can tell you what I've seen in terms of what people do as a data science scientist. And then we'll go on to talk a little bit at the very end about this crazy startup thing that I'm trying to do, why I'm doing it, and it's mostly fun. And then I'll try to do a demo here. So that's roughly the outline for the talk. So let's start with what is data science. When I was at IBM and I would go to the data science talks, by the way, awesome nerds, seriously. Most of the talks sounded like statistics to me. And I don't know if you know my background, but I'm actually not trained as a computer scientist. I've been trained as a cognitive psychologist. So I did a bit of statistics in my day for studying my own field. And I would go, wait, that sounds like statistics. Why is this data science? And sure enough, if you look at it, these terms have been somewhat conflated. And what's surprising is they've been conflated for many, many years now. It really is the intersection of these two fields, computer science, data, statistics, math. You know, you get the sense. It's a very broad and interdisciplinary field. And I think you'll see quite a chunk of each of these fields in this field, which is what's exciting about it. So I'm sure you have all heard of what data scientists do, and this is probably rather boring to you, but I thought I would just bring in a few examples that you might not have heard of. Recommendation systems, you know this all the time. You're dealing with Amazon, Netflix, etc. I don't need to tell you this. Digital advertising, it's in your face. You're on your Facebook all the time, and there you are with digital advertising. Fraud detection, that's what happens when your credit card says, company says, I'm not really approving that charge. There's really a fraud detection algorithm going on in the background that says, this is unusual. So it's an anomaly detection. That's what the algorithm is that's going on behind the scenes. Same thing with insurance claims. Not really, because we know they like to deny claims anyway. Cybersecurity, actually this is becoming a very big application of data science. As you get more and more systems and cloud services, so Amazon Web Services, Google Cloud Platform, Microsoft's Azure, all of these things are now becoming the repositories of very sensitive data. I mean, when I was in Watson Healthcare, one of the big things that we were going after was putting customer data on the cloud, and this is health data. There are laws around this, right? Just like finance data. So it's extremely important to keep the system secure and make sure your data isn't compromised or your system is not compromised. And again, they're starting to use a lot of these anomaly detection algorithms to detect changes in patterns of activity as the servers are serving up requests, so that you can find these things before they bite you. Last but not least, healthcare. It's really changing significantly. There are a whole bunch of insurance companies in healthcare who are very focused on how do I cut costs, who's the expensive patient, how can I predict my expensive patients, but on the other side, provider side as well, so not just the money saving thing, but actually saving lives. There was a very interesting application of this in IBM before I left. It was a very public statement, so I can tell you about this. It's a company that makes devices that are wearable devices that are constantly monitoring glucose levels. This is in diabetes kids. And what happens is that because you have changes in activity of children, for example, they have their insulin shot, which is what they had yesterday, but they then end up hypoglycemic. And so there are predictive models that are being built to predict that, so that they don't end up in a situation where they are in ER in the hospital. So lots of different applications. This is not a comprehensive list at all. Okay, so what does a data scientist do? For the most part, you're trying to build models for prediction. That's a gross generalization, but that's sort of an 80% chance of what you're doing. But in practice, it includes all kinds of different activities which don't actually qualify for like the statistics aspects. So the first step is finding the right data. How do you actually find the sets of data that you need to build your model? That actually is a non-trivial step, even in the so-called world of free data. By the way, please stop me if you have questions as I go along. I have a tendency to kind of go fast, but please stop me if you have any questions. The second part of this is, how do you manage this data? Once you have it, how do you store it? How do you query it? What is the system that you create so that you can pull it into your analysis? There's the third piece, which is the nastiest bit by far. I actually have a box around that you probably can't see because of the way the screen is projected. The merging data analysis, the cleansing data, the finding data takes 80 to 90% of the time on a data analysis project. You're not building models for the most part. You're sitting and doing all this other stuff so you can get clean data for your analysis. Now that sounds awfully boring, but that's where the computer science comes in. And to me, that's kind of the cool part. This is the part that I actually work on, okay, and have worked on in the past. Then you have the actual building of the model. That is also challenging, so I don't mean to imply that this is just a trivial piece of work. I'm just trying to point out that the steps involved in this are involved, and the first few steps are awfully manual and painful. And then the last but not least, please.
Yes, you said you like doing the first 4 steps and you enjoyed it, and computer science comes in handy then. So how and why do you enjoy those steps? Because those steps just sound painful to me.
Hold on to your question, because once you see what we're doing, you'll see why I'm so excited about it. Go ahead.
Why would someone who has all the skills for data science to do, saying the first 80%, when you just get like a few computer science guys or entry-level guys to do the first 80% and then the big guys to do the last 20%?
Very good question, and actually I think each of these steps has a very big computer science guys doing problem solving there, and you'll see that as we go along. So on the surface of this sounds, oh my God, awful, right? I'm doing this by hand, manual, what the heck? Like, why did I get paid, $200,000 to do this, right? But the reality is, what are we really good at as engineers, computer scientists, and mathematicians and statisticians? We hate doing that stuff, so we're going to automate it, right? And so that's where the cool challenges are. How do you automate those steps? How do you actually cleanse the data without actually going through? Trust me, if you've done any of this, even for 30 records, humans are horrible at this. They're awesome at picking up language. They're fantastic at face recognition. They're terrible at any kind of manual boring activity. It takes them literally, 10 records and your eyes glaze over and your mind wanders off and you're thinking about, everything except what you're supposed to do. So, given that, and given the manual steps that are involved, how do we automate that? That's kind of the key thing, right? That's a cool challenge here, and that's why I'm excited about it. Hope I answered your question. If I didn't, I will get more specific as we go along. I'll tell you exactly what we're doing. Okay. So, the last step, very important step actually. This is another fact that I observed as I watched these data scientists. There are so many cool methods. They'll pick one. They won't do the different methods. Why? You ask them, why did you do that? Oh, because it's easy to explain the results. You're like, why? Well, why don't you pick a better method? Or why don't you get more systematic about this and do all the methods, given that we have all the compute power in the world, why not? And then figure out which one's the best. Oh, because the customer won't believe me. And trust me, the eventual consumer of your data science is another person. If you cannot explain your results to that person, you can have the fanciest model in the world, but it will be very, very hard to sell it. And if you're trying to get a doctor to buy this, good luck. Okay, so finding the right data. Why is this a real big problem? I love this cartoon, right? And you can see the humor in this. This is like, oh, I've got this data set that's noisy. Well, I've got this other data set that's noisy. Why don't you put them both? It'll be better. Big data. Big data solves all your problems. No, it doesn't. It makes the noise worse in many cases. So you have to be really, really careful about your selection of data, right? This is where the science part comes in and the statistics comes in. You really have to start off with some sort of a scientific hypothesis about what your population is and be very, very careful about picking your representative sample. Otherwise, you have a CNN moment. This is like the CNN moment. A colleague of mine at IBM would always say, you do not want to be in that CNN moment where, Jeannie Rometty or Sam Palmisano comes and says, what did you do? Right? And it can happen. This is a great example of real life choice of an unfortunate sample. That's what it is, right? You trained your classifier without including a significant percentage of the population. That's what's going to happen, right? So, I love that example. When I first saw it in the newspapers, I was like, statistics. Okay, more data finding challenges. So once you've identified your data and they're kind of connected, you also have to choose your features. You have to decide what sets of features you're going to actually use. to build your predictive model. And again, I'm focused here on prediction, but it kind of works even for classification or some of the other aspects of data modeling. So you might ask, why not throw in every possible feature? This is very common. You'll see this actually being tried by some data scientists. They're like, throw in everything. You know, the system can figure out which ones are important, which ones are not, and we're done, right? No, we're not, right? Here's the reason why. Let's take a simple one-dimensional feature. So we had only one feature here, and you wanted to classify this, these data points, reds versus blues. Okay, so the classification function came up with something that looks like this. I made all this up. It's just a little picture for you to see. Okay, but now we said, no, let's throw in an irrelevant dimension. You know, we throw this dimension. It doesn't actually happen to be irrelevant here, but you know, let's assume it's irrelevant. So there was an outlier, and so the system just says, aha, I can now build this other function. You get a lot more freedom. The system has a lot more freedom to build these different functions that separate your points, right? If you're trying to classify the blue points and separate them from the red points. And that actually has a term in the field. It's called the curse of dimensionality, right? And this really, really bites you very, very hard, especially in high dimensional space. So high dimensional space is when you add more and more and more features, right? If you have one feature, you have a one-dimensional space. You have two features, you have a two-dimensional space, and so on. You add like 1,000 features, you get into trouble very, very quickly because of this. Any questions? Yeah?
Could you give a practical example of could you give a practical example of something like just throwing all these types at it?
Okay, very good question. I'll give you a real example, a real world example. A colleague of mine was trying to predict if two drugs would interact badly to cause an adverse reaction in a person. And so the question is, okay, what are the features? You can have all kinds of features. You can have it based on the chemical structure, right? The structure of the drug. You can have it based on the particular organ that they target. You can have it based on the particular transporter that you use. The list is really long, right? And so I think he ended up with something like 1,000 features. Okay? So now we're talking about 1,000-dimensional space. Okay? And in his case, he was using, I'll talk a little bit about this in a moment, he was using a model that doesn't have as many, freedom, that doesn't have as much freedom to fit the function. So he was okay. But if he tried a different approach, his performance actually gets worse. You try a more powerful model. You try a more powerful model that can fit any kind of function, and it actually gets worse. Because what's happening is you have way too many different types of functions you can build for the same data. It's very sparse. Imagine you're laying it out in space. It's a little hard to imagine, but let's say you put it out in three-dimensional space, right? Your data is very, very sparse. You can section it however you want, right? And you pick the wrong section. Now you've built that model, and you go and you say, I can predict this in the real world. I can set it up in a hospital system, and it doesn't work. Okay, so that's what's going on. Did that help? Okay. Oh, yes.
So this is the same problem, if I'm understanding correctly, as drawing the target around the arrow. The problem is you shoot the arrow, you draw the target around it. So if you draw a really nice target, you fit it very well, and you shoot the next arrow, it won't tell you where the next arrow is going to go because you drew the target afterwards. This is the same thing. You're drawing the function around the data you already have. If you want it to be predictive and it's too accurate, then it won't be related to what's happening.
We will keep coming back to that theme over and over. It's called overfitting. It's a standard problem in machine learning. And yes, you will come back to that problem. In fact, I do have a picture of a target even. So, I kind of had ESP. I definitely foresaw where this is going. Okay, so I'm going to switch now to talking a little bit about managing your data models. And this, take with a big grain of salt. This is my own opinion. It's not something that an expert would say. There are a whole bunch of different systems out there. I love this cartoon, by the way. If you've never seen it, it is the geek cartoon. What it is, if you can't see it back there, is this person says how to write a CV. And so one guy says, do you have expertise in SQL? The other one says no. Says, doesn't matter, right, that you have expertise in no SQL. Which is awesome, I love it. So, whole bunch of different systems. I mean, if you roll back to about 25, 30 years ago, there was relational databases, and you're done, right? Now you have a whole plethora of different kinds of systems. You have key value stores, the good old relational database, which will not go away anytime soon, no matter what they say. Column stores, document stores, graph stores. Don't get me started talking about that, because that's my passion. This talk will become a graph store talk very quickly. And also systems that actually deal with streaming data, so event streaming in, like the systems that, events tracking that, for example, you might use for cybersecurity. You're just constantly monitoring systems. That is a streaming sort of system. So my personal view on this is that one of the things that has changed significantly over the past 5 years is that there have been a tremendous growth of cloud-based services that do all of this stuff. Every one of these stores is provided by every one of the major vendors. And so there's less need, in my view, for the data scientists to come up to par and come up to speed with each of these different kinds of stores. Yes, you have to know how to use it, but you're certainly not going to be sitting there and even deploying these systems anymore, which if you have ever, Judah, I know you're in distributed systems, but if you've ever done any of these deployments, trust me, it is painful. And what's more painful is getting it working, because you're like, what? Why did you blow up? I don't know, because the system didn't ping that one. Very, very common. So it's a good thing, I think, from my perspective, even though I'm a graph store person, that these cloud management systems are becoming very, very common, easy to use, and cheap. So I would encourage you in your jobs to think of these before you go off and roll your own store. So I just want to say that. That's, again, a personal opinion. You might disagree with me. Okay, let's get to the more fun stuff. Merging data. So all the features that you want when you want to build your model are rarely going to be in a single silo. In fact, it's exceedingly common to have situations where you want to integrate across many, many different kinds of data sets. And so you can do this at the schema level, right? You can say, okay, is this column in this table the same as that column in that table, and merge it, right? And you can try to do that, but it's very, very hard to automate. And here are some reasons why. First, database people are just evil. They never name names, nicely. It'll always be something that's very obscure. You look at it as a human being and you have no idea what this is, right? So that's common. Partly it's because some of these databases are very old and there were character limitations on the side, the names of columns, the names of tables, the names of everything. So everything is as obscure as your code variable names, which you know what that means, maybe, but nobody else does. Okay, and even when they are the same, they can mean very different things, right? So you can have somebody very nicely call something a date. Wow, that doesn't help me. Is that a start date of an employee? Is that the death date? Is that the birthday? Who the heck knows, right? And then my opinion, in my experience, documentations about schemas is never really in a machine interpretable form. Usually, if you're lucky, they'll give you an Excel spreadsheet I don't know about why Excel is so dominant. I really do not. And then somebody sits there and actually tries to make sense of these Excel spreadsheets. Otherwise, you're unlucky and it's in PDF, which is even worse. So pick your poison. Now we get into the more interesting problems. To me, the schema element problem is not one that's easily solved because, as I said, for some reason, people don't tag these in a machine interpretable way. There is a relatively easy solution to it, but people do not adopt it, and I don't know why. The other problem occurs at the instance level, and this is something you all probably can relate to when you've gotten 5 different advertisements to get the same credit card from the same customer, right, or from the same company. They can't resolve you. You exist as different people to them, right? And the reason this is hard is that you get these different variants of a person's name across different data sets, right? And worse yet, you might have the same entity information but spread out across different columns. So that's an address, but it's spread across 3 columns in one case, or 2 columns in one case, and 1 in the other. Very hard problem to merge, right? There are some very interesting techniques coming on now to try and solve this kind of problem. So one paper, one study that I'm going to talk about actually came out of Microsoft this last year, 2015, ULDB, where they were basically looking at the enterprise data as a large corpus, so across tables. They're observing row-wise correlations. So let's say in a bunch of tables, Microsoft appeared with MSFT, which is their stock symbol, right? Then they can say, aha, those two are semantically related. And so the next time they see MSFT and Microsoft as 2 things in a different table, they can actually do a semantic join. And semantically, the same entity, well, one's the stock price of the other. But it's a useful way to merge things. So I don't know if I answered your question or not. Somebody that you asked me, why is this interesting? Why is this something that you want to work? Yeah, there you go. Yes, this to me is exciting, right? I mean, VLDB is a top-notch conference of databases, and they're doing something very interesting with solving a very hard problem, right? Again, using other correlations in the data to solve. How am I doing on time? I'm sorry. Okay. All right. Now back to the mapping the schema elements problem. You can actually build some degree of automation into this. One thing that was tried a long time ago, that's a very old system called Clio, is that they would try to take different kinds of, they try to take the name of the schema element, the type of the schema element, the kind of data it has, like the actual instance data, and then try to figure out the mappings and also add learning algorithms in there. So this is a fusion of the sorts of techniques that have been tried in the space of schema mapping. And what we did, this is actually our own work, the Helix system, is we said, okay, let's just take a slightly different approach to this whole problem. Let's say you had 30 million web tables and you wanted to find all the columns that mapped across them. How do you figure out which ones are about schools, for example? We decided to sort of say, okay, let's take a look at all the string fields or string columns in there. Those are really hard to map, right? But they're the ones that tell you something about the entity. So we took an approach where we said, okay, let's just take a look at all the terms that are there. We're not focused on the actual names of entities there, but more like the actual words that are there. And the observation is that if you have a column about bank organizations, the term bank will dominate. It'll be one of the higher ones, right? Incorporated, limited. These are the words that are going to come up to the top. So you can use that sort of term frequency and algorithms from document similarity to start doing this massive connectivity across tables. And that was actually the Helix project that Tudor talked about. So that's another kind of approach you can take to solving this problem. Yeah?
What about an approach where you look at when it was modified? Like a lot of people are entering the same number at the same time. It's quite, even if it's an integer, it's quite possible they're related. Even if it's an integer or a decimal. Like let's say the stock price changed. A lot of people enter the same stock into different tables. You should be able to connect them because they enter the same number at the same time.
Yeah, that's sort of the similar to the sema-join idea, that you got these relationships. After all, tables are nothing but relationships between entities and other entities. Here, the stock price of a company, right? So what they were trying to do in the sema-join project is observe those correlations and then build a connectivity based on that. Yeah, that's very much doable, I think. Yeah, I mean, this field is ripe for ideas. If you have one, start a company. Okay, so next step is data cleansing. So again, data can be terribly noisy. This can be noisy, even a single source. We had, I should probably not be saying this, a very large company, and their problem reports was one that we had access to. And you will not believe the degree of noise in that data. This is our customer-facing thing. You need to understand problem reports because you have to service them. You would think that that data set would be cleansed and really clean, but what we observed was that a column would get hijacked. You would start with a column meaning something, and then it would evolve to something else, and people would put in random rubbish in there, and at the end, you're going in as a data scientist, you go, but, this is common. Simple examples in a single source, illegal values, right? You can't have 30 as a month. It's a really simple example. Here's another one. You have an age of 22 and a birth date or something else. We had patient data, and they apparently died before they were born. And stuff like that happens. You can also have uniqueness violations, which are more subtle to detect. If you have social security numbers, for example, the same person has two social security numbers. That's another example. Or you can have, this one is the hardest to detect, is your reference department is just wrong. Well, how do you know that? Unless the department is not a valid number, it's very, very hard to know. So some of this knowledge, and typically the products in the space have taken the approach of building in rules and saying, hey, age and birth date, those are related, and so on and so forth. And I think one of them is supposed to have 200,000 rules for this kind of detection. Now this works fine if you have essentially declarative knowledge. That is, example of age and birth date is a great one, yeah? I mean, there's no probabilistic thing about this. But in fact, a lot of the rules are really more probabilistic. Like, does John Smith refer to the same person as John L. Smith? I don't know, right? I don't even know as a human. So no system should be asserting that is in fact true. That's bad. So it's hard to actually do that using that kind of approach. All right, I'm going to switch gears now and talk about building models, which I think was the 20% that was really awesome and you wanted to focus on. So we're getting to that, okay? So I'm sure you've all seen this before. You have kind of many different ways to slice and dice the different types of models. But for the most part, people break it down somewhat like this, right? So you have supervised models, unsupervised models. Within supervised, you have regression, where you're predicting some sort of a numerical value, or classification, in which case you're predicting essentially a discrete thing, like, oh, that's a cat, this is a dog, this is a face, etc. So there are many, many different models for each of these. So I don't want to pretend there's only one, right? But the job of the data scientist is to figure out what might be appropriate here. And the one thing that I really related to is this really, really famous data scientist called Pedro Domingos. If you ever get a chance to look at his videos, lectures on YouTube, I strongly encourage you to do that if you have any interest in it whatsoever. And he says something really important which most data scientists don't seem to want to do in practice, which is don't get attached to a model. You have to try different models because there's no such thing as one model is better than all other models. It really depends on the problem that you're trying to address, which one is. And in fact, one interesting thing that actually makes it easier for you to try all these different models is that Google and Azure, Azure, Microsoft Azure, and I think AWS now, they're all trying to black box the process of choosing models. So pretty soon, the data scientist's job is going to be automated. What they do is actually behind the scenes try all kinds of different models on your data and then pick one based on your the performance of the model on a test data set. So at least that's my guess about what they're doing. That's sort of where people are going now. Yes.
So if you said the data science job is going to be basically replaced by computers or whatever models, does that mean people in data science don't have jobs anymore? What's going to happen?
Great question. I don't know the answer. It's too early days. The classification service came out last year. I haven't tried it. Ask me about 2 months later because I am going to try it. And the answer is, I think, no. You're fine. Machines are not going to get rid of you. Okay. So regression, a very simple example. You probably remember a lot of this from your high school math or something. So if I'm going over stuff that is just too simple, say please move on, okay? The reason I start with regression is it turns out to be kind of the basis for a lot of stuff. Logistic regression, which is a classification, is built off of this. A lot of neural networks are actually built off of this. Deep learning is based on this, etc. So what's going on here? You have one feature, this lovely little example that I drew up in Excel with how many of our data points, 5, 6. Don't ever do this in your real world, right? Fitting a line to 3 points, not acceptable. But what you're doing is you're trying to fit a linear function that minimizes the error in prediction. And that colored line, red here, is sort of what you want to minimize. There are really only two parameters for this model. That's the slope and then the intercept. That's it, right? You're done. You define the line and you're done. And you pick the parameters that minimize the total error, actually squared error. Your cost function is the sum of the squared errors across all your data points. And your optimization objective is to minimize that sum of squared error. Okay? Now, what if your data was actually not at all linear? And in fact, it was more like this. That's my attempt to run an Excel, so apologies, right? Well, maybe you can do something more clever. And you can say, wait, I actually think this looks more like a parabola. Maybe I want one more parameter, right? And I'm going to make that parameter x squared. So I'm going to have A, B, C. Those are the 3 parameters I'm going to learn. And I have a nicer function, right? And yes, you can most definitely do this. But let's say you decided that actually that function was more like a 25-degree polynomial, right? So then your function looks like this. Keep going. And you have to pick 26 parameters now, right, to minimize the total error. So you can clearly fit any set of points with 25 degrees, given that you have only like 5 points. Yay, right? Sparse data, lots and lots of parameters. Awesome, we're done, right? But you can tell what's wrong with this picture. And one of you, I think, brought this up earlier, right? Trying to remember, was that somebody that's you, right? You're back, right? So the issue is whether this will generalize at all to data. And this is something that is like completely the most annoying thing about data science models. Yes?
How do we decide like to what degree we're doing this? We just decide that there's 25 parameters, 26. Sorry. How do you decide there's 20? How do you just decide 26 parameters? Why do you? What's the? I don't know.
How do you decide when to stop?
How many parameters
Yeah.
to go with?
How do you decide how many parameters exactly? How many parameters you?
Yeah, get into that in the next few slides.
Okay.
Because we're basically saying it's a very difficult problem to avoid overfitting. There are ways to combat it. There are many techniques that you say, okay, I'm going to throw in this as a penalty, effectively, right? There are penalties for when you do your optimization function. You can add things, parameters to say, okay, I do not want to overfit if I can. But it is hard to do. And what you normally do is you withhold a small amount of data that you don't see, the system doesn't ever see, right? And use that to validate. So what happens is when you're building the model, there are these approaches which kind of do, build on some subset, test on this other subset, see if we're like close to overfitting or we think that it's not generalizing well, then do that iteration again with a different subset. So it's called cross-tenfold validation or some variant of that. Effectively, what you're doing is you're using a subset of your data hidden to try and figure out whether you might be overfitting. And you stop well before you overfit. That's one simple example, right? Which will answer your question. Okay. Tenfold cross validation. That's right. Didn't get it when I was talking. Okay. So this is again Pedro Domingos, the person I told you about, an awesome paper called "A Few Useful Things to Know About Machine Learning." Citation Classic, 500 plus citations to this work. And here's sort of the main point he tries to make. You're always sort of trading off what he calls bias, what is called bias. That's a tendency of the learner to learn to consistently learn the wrong thing. If you think of our linear function that was trying to fit the data, it's trying to learn the wrong thing. It's always trying to build a linear model, right? And the data is non-linear, so you're kind of never going, no matter how much data you add, you're never going to get much better, right? Versus variance, where you have a more powerful model, right? It can do more like complicated things. It's not restricted to linear functions, but it has a lot more variance. It's going to pick up random stuff in the data and build really randomly. I mean, it will be very focused on that. So there's the target picture I talked to you about. This is sort of your ideal model. You want low bias and you want low variance, right? You want a very powerful model that doesn't tend to overfit. Very hard to do, which is why your job is going to be fine. Okay. The other, go ahead.
Isn't it sort of definitional to that ideal that you can't overgeneralize it? It has to be specifically contoured to each problem.
Can you come again? Which part of it do you think?
The modeling itself. I mean, you can't make some magical program that you throw a problem at it and it'll give you back the perfect model. You have to design a model for every single problem.
I believe that is really true. Yeah, I believe that is true. I was trying to tell you a trend that I'm seeing in the industry, where they're definitely saying, throw in any data and we'll build you a model. I'm serious. I mean, you can go to the Google Cloud Platform and go to the classification thing, and it says you can build it for translation, it can build it for whatever you want, basically. Just give it to us in this format, and we will return you a model. As I said, ask me to, a month or so, because I'm about ready to sit and evaluate that. Because, as a scientist, the first thing you go is, well, yeah, right. I buy that. So, yeah. There are really interesting papers, though, that are taking sort of interesting steps towards automating things. So I remember Horst. Did you know Horst? There's a colleague of ours at IBM who did some very cool work that said, you could take small subset of the data and estimate how well you would do eventually, right? And then sort of pick it's a sort of a greedy approach. You give that model that's doing potentially on a good trajectory more and more data till you finally saturate it, and you will pick the best model. So there are interesting approaches in the works. Do they apply to every kind of model? Absolutely not. Horst will be the first one who will tell you that he can't figure out how to do neural networks because they are like, it's crazy. I mean, it's an architecture. You're not choosing any features, so you're completely host. You have no real control of those systems. So again, your job is fine, as long as you go into deep learning. No, I'm just kidding. Okay, I'm gonna, do you know, how am I doing with time?
Like 5 or 10 minutes.
I have 5 or 10 minutes. I'm going to skip the other kinds of models, the unsupervised models and classification. Classification, same thing, but you just, decision trees, super common, used very heavily, right? If you think about what they're doing visually, because I'm a very visual person, I love how to see things visually. Basically, they're dividing up your space into these rectangles that are axis parallel, right? So clearly, you can learn things that are kind of more clever than a linear function, right? And ultimately, you're not learning a function; you're learning a set of rules, a tree of rules, right? So I just wanted to throw it out there. I'm going to skip clustering. You can look at that very nicely in Wikipedia. And I'm going to quickly get to explaining predictions, which I don't want to stop because this is a really cool paper that just came out, KDD, another top-notch conference, 2016. And so I want to, before we get to the actual algorithm, which one, so this is an algorithm that's trying to learn atheism, okay? It's trying to classify documents or emails by whether that reflects atheism. And which model would you predict is better? This one that says the key words that are important are God, mean, anyone, etc. Or posting, post, RE, etc.
So obviously the first algorithm.
Obviously, right?
I was just going to ask a question also, what's the green versus the pink?
I
So
don't-
God, mean is pink versus anyone this.
No, I don't remember honestly what the coloring was about, to be honest.
But the answer is the algorithm one.
Yeah, algorithm one, but guess what? The other one was better in terms of the training data, right? The other one was actually better in terms of if you just looked at the usual metrics for how did the model do for training data, right? So the point of this system is really, really neat. It says it doesn't matter how complicated your classifier is. So this classifier, I don't know if you can see back there or not, it's got this shape where, it's got red in the middle and blue on the outside. And, it's a very complex function. It's definitely not linear, right? But what they do is they take a point that they're trying to explain, and then they take the points just around that point, right? They're very close to the point. And they fit a linear function with very clear features that can be explained to humans. And then they've shown how nicely the system does, not just on a classifier with words, but also on images.
It kind of looks like an SVM.
This one, I don't know what the original thing was. This is just a diagram. It's not meant to be a specific model. Okay. But the point they're doing, I want you to get that idea clear. That is, even if your classifier or your function is a really complicated beast, you use a very simple linear model that can be easily described to approximate the area just around what you're trying to explain. And it turns out, and this is a really nice example of image data, right? So this is Google's inception network, neural net, which is like impossible to understand what a neural net is doing. The top 3 classes are predicted with electric guitar, but you can see they actually had electric guitar, acoustic guitar, and Labrador. And each of the pieces and why the system chose that class, if you look at it by pixels, you can sort of see why it's doing what it is, which is very neat. I think that's a very powerful way to think about how to explain things to users so that they know what the model is doing. It's also useful for debugging the model, right? Remember we said about irrelevant features and overfitting? Here's another great way to look at it. Because that first model is one I would trust. The other one, forget it. So, yes?
So what was the name of this paper?
It's called Lime, and I have the reference down here. It's hard for you to see, but it's Ribeiro 2016, and it's a KDD paper. It just came out. Okay, so that's a University of Washington group.